In this video, we're looking at problem 5 from practice exam 3-1 in the fall 2021 semester in Chem 1211. And the question is, what is the total number of orbitals in the n equals 3 and n equals 4 energy levels with L equals 1? Enter your answer as a numeral. So I see n values, I see L values, I'm thinking about orbitals. This is a quantum number situation, quantum number problem. And specifically, it relates to the constraints or rules for quantum numbers. How is the number of orbitals constrained or limited by the L value and by the n values that are allowed right here? So essentially, I think the best way to proceed is list the allowed sets of quantum numbers based on what's given in the problem, and then try to unpack those into a number of orbitals using the rules or constraints for quantum numbers. So let's do that. We've got two allowed values of n based on what's given in the problem, n equals 3 and n equals 4. The L value that is allowed, or that we're interested in both cases, is L equal to 1. And now what we want to do is take those sets of quantum numbers and deduce the number of orbitals within the subshell specified by n and L. Keep in mind, the principal quantum number and an orbital quantum number specifies a subshell. 1s, 2s, 2p, 3s, etc. And let's actually start by unpacking that subshell label from the given quantum numbers, giving us something that's a bit more human-friendly, shall we say, to work with, rather than these sets of numbers. So n equals 3, L equals 1. What is that as a subshell label? Well, L equals 0 is S, L equals 1 is P, and so n equals 3, L equals 1 corresponds to a 3P subshell. Likewise, for the other set of quantum numbers, n equals 4 and L equals 1 corresponds to a 4P subshell. Now, if you're familiar with orbital energy diagrams, that kind of scaffold of atomic orbitals that we use to construct electron configurations for neutral atoms and monatomic ions, then you already know how many orbitals are within each of these subshells. But if you don't know that, a way to proceed kind of analytically, systematically, is to think about the rules or constraints on m sub L based on the value of L. In other words, what are the allowed values of m sub L given that L is equal to 1? Well, m sub L must have an absolute value that is less than or equal to L. So the allowed values of m sub L for L equals 1 are -1, 0, and 1. And in fact, that exact same set of values is allowed both in the n equals 3 and n equals 4 shells. So I'm going to go ahead and copy and paste that since it actually applies to both of these subshells. And I can immediately conclude then that there are 3 orbitals within each of these subshells. And again, if you're familiar with electron configurations and orbital energy diagrams for atoms, you kind of knew this already, but the m sub L allowed values tells me there are 3 orbitals within each subshell. So we might, on an orbital energy diagram, draw the 3p level with 3 horizontal lines like this, indicating 3 orbitals, and the 4p level with 3 horizontal lines like this, again, indicating 3 orbitals within that subshell. And each orbital, by the way, is specified by 3 quantum numbers, n, L, and m sub L. Each has a unique set of those 3 numbers. So, of course, counting the number of horizontal lines I've got, or counting the number of allowed m sub L values across both subshells, I arrive at a total number of orbitals that is equal to 6. And there we go.